Welcome, everyone. This is our first episode in a podcast series where we would like to touch on topics that can be interesting in terms of computer vision. And today I'm talking with András Horváth, our professor here at Pázmány University. My name is Kristóf Karacs, and I am the head of the IPCV Master Program. Hello, András.
Hi, Kristóf. I also want to greet everyone from here. It's great and an honor for me to be here, and I hope we can discuss some interesting topics.
So for today, we agreed that we would touch on some of the most interesting aspects of neural networks in computer vision. And as one of the core competence of the faculty is realizing efficient chips for not only vision, but also for other purposes. I think we could start by discussing what is the current vision in terms of the neural network community or computer vision community for efficient computing, especially for maybe even targeting chips or hardware devices.
Well, yeah, it's a really interesting topic, and I think there are many aspects of this. So I think first it's undeniable that computer vision was changed by machine learning and artificial intelligence, and there are new applications which we couldn't really done or maybe even imagine that it will be solvable with computer vision a few years or a decade ago. But on the other hand, as this was clear from your question, that's also true to train these methods and also to even just to run an inference and use them in practice. These algorithms usually require a lot of energy. So, for example, if you check current implementations, there's NVIDIA have this Drive PX machine, and they are very self-driving cars. They are solving problems, which is great. But usually, these devices cost more than the actual car, and even the power consumption is significant in terms of that. If you want to use an electric car, it will seriously affect the range of your car. So there's a really strong need of creating efficient implementations, and from biological motivation, and in which our faculty is, I think, really good, because we try to focus for even early years on neurobiology and how human vision does the same task. We can know that these can be solved extremely efficiently, which we haven't learned at all from these systems. Because if I eat a sandwich a day, I can go out and recognize the cars on the street. So I think there's a lot to learn there. Regarding efficient implementations, I think there are two different ways and two different paths in these aspects. One might be that I think there's a historical strange phenomenon that as these methods were introduced to the community, everybody was really happy that, oh yeah, we can learn with a convolutional neural network, we can learn tasks like never before. But nobody really cared about their efficiency, because if you check them through the years, it turned out that for training we need floating point accuracy to train them, because we want to differentiate them back and calculate the gradients. But then turned out that we can quantize this. You don't need the floating point accuracy for inference, and people started to use fixed bit precisions, and turned out it's enough to use 16-bit precision instead of 32. Then now almost everybody uses 8-bit precision, which is enough for most of the practical applications. And there were really extreme companies like Exnor AI who introduced 2-bit or 1-bit precision, whether a bit can be 0 or 1, and was still enough to do this. So I think that there's a lot in this aspect to really more efficiently implement these ones. The other is that we have a lot of filters in these networks. Even if you use transformers or convolutional networks, in one layer you extract 256 or 5,000 or 500 or thousands of features, and nobody really cares about the correlation of these features. You just initialize them randomly, they will move in some points, and many times 20% 5% or 10% of the kernels are really similar to each other, and they don't have like added value. There were some nice papers coming out in the last years which were called like neurorejuvenation, when you just throw out the insufficient kernels, which we hope like in our vision system was somehow like thrown out over the years by evolution, and then substitute them with ones which do something else randomly, and maybe they will have like some added value in the whole network. I think this is one really good and interesting pathway, which we also like partially try to work on. The other part is, I think, the implementation of actual devices, that how can we do this computation, and this is, I think, partially like driven by computer vision and artificial intelligence, but this is a more generic phenomenon that in the next few years will be like really interesting in computer science, because we are getting closer and closer to the edge of like or to the end of Moore's law, when we can just downscale transistors, and something else should be used for that. We don't really know what. There are some like magnetic calculations, a lot of people working on quantum computing and other things, but like the most guesses are towards like some sort of analog computation, where instead of like using like bits which are like binary, we can use some sort of continuous ones. And it's really interesting also in our vision system, as far as I've learned, that we can debate whether like we see in an analog domain or a discrete domain, and how our eyes see, because we have like synapses, and you can think about a synapse, and usually that's the model that it either fires or it doesn't fire. But like in our retina, we have electric synapses, which are like more closer to like the continuous domain and connections. So I think like these are the two more aspects, that there's a lot of things to be like more efficient algorithmically, and there are a lot of new hardwares, and I hope that in the next years there will be efficient analog implementations for these networks.
Yeah, the interplay between these two fields that you mentioned will be extremely interesting in the upcoming future. And the topic, like the evolving new prospective architectures and implementations would be worth a complete new discussion. So we might go for that on another occasion. However, what I wanted to ask you about is, in terms of implementations, there are some companies who have enough resources to build ASIC solutions, like Tesla, for example. And how do you see the landscape in terms of energy efficiency and flexibility to be prepared for future generations?
Yeah, I think this is also another really interesting question, and more on the side of flexibility currently. Probably also because I do research with these architectures, and we don't really know what we want to use and plan to use. That's what we're like currently working on, to find the proper architecture. And I think an ASIC implementation comes after, when you know, like, this is the algorithm I want to use to solve the problem. And in that way, I think that's great to like use these ones. Also, I mean, like Tesla and other companies, I think they had to do something. They had to like put an efficient chip in their cars, and maybe other devices if they will have robots and other tools in the future. But I think that's also more of a constraint for them. That, as I've seen, that they are now constrained in what kind of networks they can put there, because on one hand that's good, because then they have to like consider energy efficiency, but honestly, like, I wouldn't care how efficient the system would be until it's safe, that it can drive me from point A to point B. So I really think it's great that these systems are flexible. And also, I mean, like, if I would go somewhere, I would go somewhere in the middle, because in GPUs you have like the ultimate flexibility, and now you have all the frameworks that you can just write code efficiently and fast in Torch or TensorFlow, and that's wonderful. On ASIC it takes like months to create like an actual device, or even years. But if you have some solution, and like, you know, like the, I don't know, like give some estimates what kind of resources you will need there. I think like another interesting aspects is the implementation of FPGAs, because like when like the whole popularity of GPUs started, everybody was doing them, and like people sort of like forgot about FPGAs. As I see in the community, people start to like realize again that it's a good common point that on an FPGA you can still write software, still write an algorithm, not that efficiently, but still fairly easy to do that. And it's true that they are not that generic, not that easy to program them, but you can create like that's especially good and efficient hardware via an FPGA, and that's also something like at our faculty we have some expertise. So I think that's maybe because of this I'm a bit balanced, but also I see in the literature that that's a way to go, and that could help, I think, before an ASIC implementation.
Yeah, especially since high-level synthesis has kicked in for FPGAs. Yeah, that was probably kind of an avalanche, and basically every 5 or 10 years, FPGA people programming skills have to be renewed. Yeah, it will be very interesting to see what comes up on that side. There's another topic I wanted to ask you about. So, okay, let's imagine that we already have efficient networks and implementations, and that is absolutely fascinating. What things become feasible by computer vision that were unimaginable beforehand. And I think most of us were amazed at some point, and then you start realizing, okay, but there are other questions that have to be after this first amusement point. And yeah, for some people this has been just recently, for others it was years ago or maybe even a decade ago. But one pushing question that is kind of constantly present in computer vision and also for the machine learning community is that once you start seeing these marvelous things appearing as a result of these networks and models, you also start realizing that the errors they make are not typically the ones that we humans make. And there's a very serious literature about the vulnerability of the models. And you yourself have quite good experience with adversarial networks. So I wanted to discuss that a little bit. Like, what are the novel points in terms of the vulnerability of computer vision models?
Yeah, so I think we have to like distinguish between two different kinds of errors. Both are really important. One is like samples which are out of like the training domain. That's still really strange, and that's where like we see that like sometimes these computer vision algorithms provide like really strange results. Like also just going back, don't want to like speak a lot about Tesla. They had problems with like emergency vehicles because of the flashing lights. That's a known fact. They had like more than 10 accidents because of this, because they don't have those in the training data, and that's a problem. And I think it's really strange for us because we inherently have like a lot of knowledge in our eyes, even like unconsciously we have seen so many things. We know about 3D space, perspective distortion, and many other things, objects, extracting information from movements, occlusions, which are not entirely well incorporated in these models, and that's why we see like you could imagine that they are trying to classify objects which they haven't seen before, like in a sense that just only in the training data. And we have seen like years of cars and traffic, and sometimes it's obvious for us that look at that, that's a fire truck, it just there's like some flashing lights in front of that, but for a car that flashing lights could change like all the input features. So that's a really significant problem, but I think like gathering more data can solve this in the future. The other problem are adversarial samples and adversarial attacks towards these models, which are really, really interesting. And I think this is in some sense similar to like biological systems or vision system, in that sense that we also have the same ones. Like these adversarial samples are like specifically tailored samples which fool the vision system. And we have these are the same, we call them optical illusions.
Yeah,
optical
that's right.
illusions, just the same thing for our eyes. The problem is that like the set of the possible inputs which can fool the system is way larger in case of like these systems, and depend on very, very different features than in case of us, because like our vision system can be fooled easily with strong contrast and other things, because we have these rapid eye movements, and it will just try to like gaze somewhere, or it will try to attract our attention. And these can be fooled by certain patches, putting their features there, or just even adding like some special noise to the image, which will fool the classification. And luckily, these are not some attacks which you can like find in nature. So there's no problem until there are like no malevolent people around these systems. But if there are, they can easily fool this ones. And it was shown there are like white box attacks where you can like exploit the gradients of the networks, but which is like even more a serious threat, that there are black box attacks that even without knowing what's inside the algorithm, you can try certain attacks which can fool them reliably. And there are many methods to like deal with this. There are like I think different approaches. One is, which people are trying to work on, is the prevention of these attacks. So somehow making a system which is like more robust towards this, where we could just create a network where you cannot create an adversarial attacks. Unfortunately, to me it doesn't seem so that this is the way to go. I mean, like you can significantly attack the algorithmic complexity to like generate a specific attack towards a network, but I haven't seen a paper which would like, even like in this clean lab environment with like publicly available nice data sets, where you can ensure that it's not possible to create them. There will always be like some gaps in like the decision boundaries and like that, where you can do this. So I think that's really interesting. We have to understand those theoretically, but it's not the way to do this one. The other interesting thing which people try to do is like the detection of these attacks, and I think that's more the way to go. And there are some nice papers where you like try to check the distribution of the activations. There are some where you add like special layers to the network, which will try to like detect if an attack is present or not. And these are good because there are some papers, again, in a lab environment and like that, but which are like, and these are I think the most successful, when in like 80% of the cases you can detect if like an image was attacked or not. And these are like the best results. Of course, 80% is far from like practical applicability, because it would mean like out of 5 times once you would still have an accident with your car if there are problems. But that's the best. And with these detections are really nice, but there's a step missing, and we just have on this year's CVPR at a workshop a paper which like introduced sort of a new problem, because we said that detection is good, but just imagine that you detect that like there's a threat. What would you do? It means you have no information about like their surroundings. The only thing that you know is that, okay, I cannot make a decision. Like this, let's say traffic center or something is unreliable. So we wrote a paper at a CVPR workshop where we tried to do like the reversal of these adversarial attacks, like reconstructing the original sample from this one. And like the nice thing which seems there is that you can prevent them, like just in a way as you can move the class from class A to class B with a gradient. You can try to like bring it back to like all the classes, and what you will see is that the easiest is to bring it back to the original class, because that contains most of the important features already on the image. Mm-hmm. So there's a way to do this. But I think as a phenomenon, these are really, really interesting. And also what I like to also mention here, that it seems as a threat for like these algorithms, but there are also advantages of adversarial samples. For example, like the most commonly asked question, I think, in case of like applications is that, okay, like how many images you need to like train a good computer vision system. And I don't know that it's not about like the number of the images. It's like to cover the whole distribution. And adversarial samples are really good to show you like which are like the hard samples, the the difficult samples for a classification system, and that can be used. Like there's a nice paper like 2 years ago, maybe it came out, like the title is something like Adversarial samples beyond the image plane, but they didn't like change the pixels, but they changed the object in like a CGI environment. That how can you rotate your car maybe to fool the system like that, and by this you can generate like really efficient and good samples to train the network. So I think adversarial samples are really interesting. They definitely pose a significant threat which has to be solved like before like practical applications, but they can also be in certain cases like advantages.
Yeah, very interesting. And one of the most astonishing things for a human observer that tries to understand how these adversarial samples can fool a network is that we are somehow unaware to understand the inability of the network to evaluate that a certain input is somehow out of the input distribution, and how do you see that? I mean, well, one potential solution is to kind of maybe train another head to try to estimate the probability that the actual prediction is okay. Well, you could also do that for based on the predicted confidences, of course. But I mean, this is not an easy way to go. So, is there any push towards? Are there any publications on making it possible to kind of have to put this kind of sense of reality into the network?
Yeah, there are definitely some ways, and I mean, like, you know, it's always like criticize the system than to just find solution. I knew about some papers when they try to understand why these things happen, and there are some samples. So like there's a paper called like why ReLU networks give like overconfident estimations, or a title is something like this, where they show that like the ReLU in a neuron and other LUs, CELUs and other swishmish, there's a problem with that they allow like infinite really large activations for every neuron, and that's not really democratic. It means that if you put a strong feature somewhere, one neuron can tell you that, oh yeah, I'm pretty sure that this is a car, and meanwhile like 100 of neurons would say, no, I think it's a dog. That neuron will win, and that's a problem. And people try to like somehow solve this problem, mitigate it with banded activations. We also did research in this, but it turns out that these also affect the accuracy of the networks partially. But there are ways like to somehow solve this. The other problem which is there is like the softmax activation, which we typically use for like classification, and that's a nice normalization mathematically, because like from an arbitrary vector you create probabilities. But with the problem is, if you think about that just about two classes, you will lose like distances in that one, because you will just say that, okay, with probabilities you will say what's the probability of belonging to that class, and it's not like a distance measure in a metric in a feature space that with like a binary classification, if you get like it 50% of a chance that this is a dog or a cat, you don't know whether it's like both simultaneously because it belongs to both classes and there's a cat and a dog on the image simultaneously, or neither of them. And this is like from classification task, this aspect is completely missing. There are some nice tries for this, like I think like the important thing is, which is I think a key for like the whole computer vision and machine learning, is that to find like meaningful embedded feature spaces. And there are like with autoencoders, there are like people working on the disentanglement of this one. With GANs, people working on the inversion of GANs, which like do like nice mappings, but they sort of don't exist. I think like one nice way to do this, like this is one of my students know, one of my favorite architectures is like the matching networks, which is used for one-shot learning, and this was, and they want to try to like solve the problem as a classification, but like as mapping this to like previous anchors with distances. And like these architectures solve this problem, that you will get a distance like how far is this image from being a dog, and you can tell whether it's like in the middle of a dog and cat class, and maybe it's in both of them, or like really far from both of them, and it's neither of them. And I think this is an aspect which we like sort of forget on the way in classification. But I think this is also natural, because we had to start with some like simple problems, and let's be honest, like classification is enough to solve, I don't know, I'm just guessing, but more than 80% of the actual problems there. But there are some important aspects like this one which will be also reflected as or come back as a problem.
Yeah, let me come to another interesting generalization, if we may proceed. Yeah, this was very interesting that you mentioned that representing the problem as a classification problem might not be appropriate in all cases. But we also know that, okay, yeah, we say image processing, but many times it's sequences of images. We actually have an image flow, and then you already have object tracking and multiple object trackings, and you know, both the location and the IDs and so on. And in those cases, out of just basic physical laws, we can deduce easy constraints for what may happen and what may not happen. So one of the challenges that of computer vision and modeling them with our current architectures is that embedding constraints into these networks is not trivial at all. So coming to the platform of logic, where you can make high-level inference based on these constraints, is not trivial at all. How do you see that?
Oh, well, yeah, I completely agree in this, because I mean, like, I've seen at a smaller conference a paper where people were trying to like train machine learnings to understand physics, and everybody was there like no, you don't want to learn this. There are the rules there. It's way easier. We don't want to solve this for all kind of tasks. And I think that's also like we have to go back to history, because like as I've seen in computer vision before the deep learning era, everybody, including me, did that. Oh, we have these nice handcrafted features, and we try to build something out of these boxes which would solve our problem. But then with deep learning, we realized that, okay, that's good, but those already contain some sort of constraint that I calculate an edge, and that might not be optimal for that data set, that like this generic nice edge detector as Sobel or Kenny or something. And in that, it was like a new phenomenon which was like really popular, that, okay, let's not put any constraints on the network. Let's use some like generic architecture, like convolutions, fully connected network, something which can learn anything. And then it would be like really data specific and really good. And it works, like, as you see, like from the data points for challenges, also applications. These are like the best performing ones. But I think we a bit overshoot in this one, in a sense that now we don't really want to like have generic rules and powers from these networks in many cases, which would be good. Like also in terms of like the really simple rules for motions and even like the geometry describing the space in these networks, usually these are like learned from like millions of samples, which we use just for this to, okay, you should understand like that there are some strong correlation between the two consecutive frames, and we should be able, I think, like now we're on the side where we also want to like give them like, okay, we will show enough data and the network will learn this. And I think that's possible because also we somehow learn this, but that's not really mathematical. For me, this is like really biologically motivated. That's how we and children learn these things. But when you go to the university and you understand physics and all these things, how they work, I think that's a higher level abstraction, which also means like higher level of generalization power and also more efficient, because if you understand the thing instead of just deducing like correlation from the data, you can apply it, and you will also know like under what conditions you can apply that. And I think that might be a really important step in machine learning and deep learning, if somehow we can incorporate like these knowledges in these networks. But unfortunately, I'm not aware of like any good solutions for this, or I haven't seen papers where you can just easily put these in the networks and somehow tell or put some constraints on the network that now you can only just create, I don't know, scenarios which obey the physical laws and make predictions. I don't know, in case of a car, which should be like real and should follow like the I don't know, rules of gravity and acceleration and others. But yeah, if this is definitely a way where these methods could be improved a lot. I don't really know how. That's the problem.
Yeah, we don't. Yeah, that's why computer vision and machine learning can be so interesting these days, and there are many open questions. I think that probably the layers of abstraction that are building on top of each other will somehow have to evolve to a point where this kind of abstraction will appear in the architectures, and we'll somehow be able to interact with the lower levels. However, yeah, the possible ways to implement this are so many that it's not easy to say how it's going to happen. And also probably the speed. So we have present-day computers are very efficient in terms of if you have just a pure logic or constraint-based system. I mean, they are way faster than how humans we are able to simulate those or any living creature. However, we are still able to do these kind of calculations or inferences, but kind of like as if it was in a simulator. So you are like simulating the digital architecture with your brain, and that's why it's kind of much slower. But if in case you need that kind of constraint, that okay, I saw the cat there, so it cannot be here because it's not possible that it's bilocating according to my observations and also the physical laws I learned in first year of university or maybe even in high school or elementary school. But yeah, so these should somehow be showing up if we go ahead. So Anders, thank you very much for coming today, and I hope we can continue later. The actual implementation of these podcast talks is still under consideration, and we hope to have some other guests, and maybe at sometimes we could even sit more people together. But we will see how that turns out. But I would like to really thank you for coming today. And I would like to thank everyone for watching us. And the IPCV program is one where you can learn a lot about computer vision. So this is a program between 3 universities. If you are interested, please visit ipcv.eu.